In this video, we're going to talk about what makes something easy or hard to spin, and that's this concept of moment of inertia. So real quickly, let's review inertia from linear kinematics or linear dynamics. Recall that inertia is an object's resistance to changes in motion. For linear motion, this was equal to the mass of the object. So an object with more mass had more inertia. That's where we had that equation, net force equals mass times acceleration. In this case, the m was representing the inertia. So now if we talk about spinning, it's a little bit different. So the moment of inertia and it's a phrase that we use kind of all as a collection here, is an object's resistance to changes in rotation or spin or rotational motion. Use the term angular. All these we kind of use interchangeably in physics, but angular would probably be the best term here. Changes to angular motion. Not only does the amount of mass matter now, so like before, the amount of mass matters. The more mass you have, the harder it is going to be to spin it. But also how that mass is distributed throughout the object. And we'll talk about specifically the way that we talk about distribution later. So the variable is a capital I for moment of inertia. Capital I, I'll put a little lowercase I so it's a little bit easier to tell that it's an I. The units for moment of inertia are kilogram meter squared. And there is an equation for calculating it, but we're not going to use it in this class. We're only going to talk about moments of inertia qualitatively, comparing them. Or if you need to use it for a calculation, for the one equation that we'll have that has moment of inertia in it, it'll just be given to you in a problem or you'll be asked to solve for it. So you don't need to worry about how you would look at an object and figure out what its moment of inertia is. We're only going to use it in a few cases. So the moment of inertia will increase, or objects have bigger moments of inertia if there is more mass, so if mass increases, or mass is moved away from the pivot point. Or their axis of rotation. If it's already rotating in a circle, we call it the axis of rotation. And obviously, if you do the opposite, you'll get it to decrease. So if you bring all the mass in towards the center, or if you decrease the amount of mass, the moment of inertia will decrease. The higher the moment of inertia is, the harder it is to get it spinning or to stop it from spinning. The lower the moment of inertia is, the easier it is to get it to spin or to stop it spinning. So two quick examples. The classic example is a skater. So imagine I've got a person like a figure skater, right? And they start with their arms out and they're spinning around in circles. They've got some moment of inertia associated with this arrangement of their mass. If they go to a different formation, so in other words, they bring their arms inwards, now they have less or a smaller I. So bringing their arms in, now and again, if you're not aware of it, skaters typically spin like this. If they're spinning around any other axis, something has probably gone wrong. But if they're spinning on the ice and they bring their arms in, they'll spin faster because they have a smaller moment of inertia. And for reasons that we're going to kind of skim past here, basically they have to maintain their angular momentum, and that will cause them to spin faster. Conversely, if they're spinning like this and then you came along and wanted to stop them, it'd require less torque to cause them to stop here. and more torque to cause them to stop when they've got higher moment of inertia. Not technically, just broadly speaking though, if we're kind of skimming past, just to give the idea of less or greater moments of inertia. Another example is, imagine I've got a cylinder, two cylinders, and they have the same radius and same mass. So same R, same mass. But the difference here is one is solid throughout the center, and the other is hollow, meaning it's like a toilet paper tube or paper towel roll. The solid one, again, same mass, it's just like it's all squeezed to the outside over here, spread out here. This one has a higher / greater moment of inertia, because all that mass is really far from the axis of rotation that goes through the middle. So like if these were rolling, it'd be easier to get this one rolling, the solid one, than it would be to get the other one rolling. Because in the solid one, some of that mass is spread out towards the center, whereas in the hollow one, all the mass is pushed really far away from this axis of rotation. So this is the main idea that we want to be thinking about with moments of inertia, is just broadly speaking, if you're comparing two roughly equivalent objects, which one has more of its mass farther apart, which one has more of its mass closer in. Or if those arrangements are identical, which one's heavier, which one's lighter. And the one that has more of that mass more spread out is going to be harder to get changing its motion, either to get it moving or to get it stopped.